Hello, everyone. I'm Véronique Gendner, and I do what I call information design full stack. That is, I cover the different aspects of structure and representation of information for database structuring, programming, and script writing, web applications and digital documents creation, as well as data analysis. This presentation is about a genealogy project. Genealogy is a great use case for graphs. I mean, graphs as a structure for humans to represent themselves complex information. A genealogical search usually starts out by asking parents and close relatives what they know about our ancestors and the pictures and documents they have. That is how you may get the name and year of birth of a great-great-grandmother, for example. Later on, you may find her birth certificate and be able to complete her day of birth. Then someone in the family sends a picture where she's represented, so you want to associate the picture to her name, but you also want the picture related to information you already have about all the other people on the pictures. Which means you're facing a very common issue in information design, that is, information gets to you in a very unordered sequence, and you do not even quite know what the structure is. It's pretty obvious that a table is not an appropriate structure in this case, because for closed generation, you have a lot of information and pictures. So keeping as many slots for older generation for whom you often don't even have a name would be storing a lot of empty cells. Also, searching information in such a table would be difficult. Very intuitively, we think of a family as a bunch of people who are related to each other. And the formal representation of things related to other things simply is a graph. But you should not expect a family tree to be a strictly formal hierarchy. Lastborn sometimes marry, oh, I was a bit too quick. Lastborn sometimes marry the next generation. And if you start collecting information for your family for some generation back in time, you'll see that cousins, if not siblings, used to marry each other much more than you think. So what you need in this case is, and in a lot of use case, where you need to manually collect unordered information, is a tool that allows to manually build an expandable graph structure. So that at any time you can collect whatever you get about a person, then complete as details come in, and simply represent relations as you learn about them. TheBrain Technology has a licensed application that allows you to just do that. Let's see, here's a short demo of the brain functionalities applied to the use case. Let's say you get married, a husband and their son's name. You first create a node for marry. In the brain terminology, nodes are called thoughts. By clicking on the appropriate dot, you can pull a link to another thought. Here's a child thought of marries. Thoughts or nodes can have one and only one type that is visually associated with a text color and an icon. You can set a relation type. The node can also have parent thoughts. In the semicolon, you can create several nodes at once.
Veronique, there is only a white screen. You see this as well? Okay. Not sure if this is.
Yeah, I'm afraid maybe PowerPoint didn't like the inserted video. Let me try plan B. I'm going to. Let's say you get married, the husband and their son's name. The first creating node for marry. In the brain terminology, nodes are called thoughts. Can you see now?
Yes.
Okay. Let's move a little bit forward. No, I was too quick. Okay.
Relation type. The node can also have parent thoughts. In the semicolon, you can create several nodes at once. So parent and child relations allow to represent a hierarchical structure, which is very good because we use the hierarchical structure much more than the complexity of graphs. But then you have a third kind of relation that is called jump, and that can relate the node to any other node with no structural constraint. So you can have the hierarchical structuring, but you are not restricted to it. It is out of the scope of this talk, but I think this ability to have a body gesture that actually connects ideas with the mouse is valuable in the cognitive process by which we build our inner representation of a subject. Thoughts can also have tags. This is what you can choose to represent the fact that all these people are deceased. Tags are displayed by an icon on the thought, so you can use them to quickly visualize some information. For example, I use a tag to encode and quickly see when I'm done listing someone's children. Types and tags are encoded as nodes, so you can display them to get a list of all nodes with a specific type or tag. Then let's say you get a picture where Mary is represented, so you want to relate the picture to her. To do so, you just drag and drop the file, which will create a child to the current node with the image type. You can actually add any kind of file in this way, PDFs, spreadsheets, sound, video, etc. And you can type the code by linking it to the desired type. Here is a note editor where you can add comments. If Mary's parents also are on the picture, you want to relate them to the picture. And now that the picture is in the database, you want to relate it to every person on it. To the right, you have Charles. And as you type, you immediately see you already have Charles in the database. So you can just link the picture to that existing node. This is a very useful functionality to avoid duplicates. Now, whenever you focus on Charles' node, you will see that he is related to this picture. Then we add Julie. Since we can see he's not in the database yet. And Jules is George's brother, so let's go ahead and quickly encode that as well. Let's say this is Mary's page on Genealogy, a very good genealogy website to collect information. With this, I can add that Mary was born December 29, 1749 in Clan Frankenheim. And died November 17th, 1793 in the same place. Of course, in the real database, I also put people's last name. To keep track of the source of this information, I can just drag the URL in the web browser and drag and drop it into TheBrain. The same if this is Mary's death certificate on the Civil Register Archive website. You can even download the PDF and add it to your database, just like we've just added an image. TheBrain is an excellent user interface for manual data collection, especially because of easy drag and drop of documents and links. Anything you can put on a computer, you can put in TheBrain. So besides the graph structure, the great advantage of TheBrain is that there is no format limitation. So you can focus on the subject, put everything about it in one place, no matter the format, and then be sure of which application to search, no matter what you're looking for. It makes it easy to structure incoming information without having to follow a strictly formal order. You can collect as it comes according to your own user agenda. In this genealogy use case, for example, at some point I'm talking with one of my parents' cousins, so I want to work on the subgraph around her. Another day I'm reading historical information and I want to work on people of my genealogy who might be related to the historical figures I read about. With the brain, I can be sure to put things in the right place, and it is no structural problem if some parts of the genealogy go faster than others. To find the people you want to relate new information to, the brain offers several search strategies. So if one fails, you always have another. And easily find the right place to put new information is very important to help keep the structural coherence of manually collected data. First, you can instantly go anywhere in the graph with index search. This demo brain only contains a couple of nodes, but it is as quick in a 20,000 nodes brain. When you don't remember the name, but something related to what you're looking for, you can go to the node you remember and then follow relations. For example, if you remember Mary has an uncle, but you can't remember his name, you can go to Mary's node and follow relation. You can do this with a place, a date, a picture, anything you remember in relation to what you're looking for. The third search strategy is to check all members of a list, like children, God, tag, or type. There actually are other search strategies, but for the sake of time, I'll stop here for this introduction.
So the brain is a very is very good for local display around a node. The limit is that at points you need to get the big picture to take stock of what has been done and what can be explored further. In the brain, it is difficult to visualize distant relations, but graph visualization enables some of our specific cognitive skills that help put things together by giving them, I'm so sorry. So I was saying, I can't talk. Let's see if I have something to chew. I don't know. So sorry about that. I'll try and keep going. So yes, I was saying that visualization enables some of our specific cognitive skills that help put things together by giving them their symbolic place. Therefore, it helps understand. Visualizing how things relate actually is part of the understanding process for any subject you want to learn. Here is an example of a large visualization for all my direct ancestors, for those I found information about. If a portrait is available, it is important to associate it with the person for visual identification, which becomes essential when the number of persons in the database increases. Dates and places of birth, death, and marriage are useful to situate both people, both in time and also geographically, to see, for example, which ancestors migrated to or from my own region of origin. This is how I found out some branches of the family did not move from one village since before the revolution, when others moved to the US at the end of the 19th century. That is, if you look at them carefully, dates and places of birth, marriage, and death give you an interesting first glimpse at what your ancestors' life has been, especially if you relate parent and children information, which is easier to do on a graph visualization. And so open source Gramps application allows to produce such a visualization, but my data was in the brain, so I needed a way to automatically transfer it. Among Gramps' different possible import formats, the easiest to produce seems to be CSV. That is the good thing with the graph structure. No matter the complexity of the graph, you can always pick a selection of node labels, properties, as well as relation types and properties to produce the table structure you need. Gramps CSV import takes a list of person with gender, date, place of birth and death, a list of family objects that are created to each couple which with marriage, date, and place. We don't have such a node in the brain structure, but we'll see in a moment how it can easily be created in the Neo4j database. Finally, you need a list of relations between families and the children of the couple. Let's say we have Jean and his parents, Annie and Pierre. This is how it looks like in the brain, with the corresponding nodes and relations in a Neo4j, in the Neo4j database. The brain export has a list of nodes with a unique ID and a list of properties. Then you have a list of links with the ID. Here comes the relation I was talking about a moment. I thought they would come earlier. So now you have the relation, the node, and the JSON for the links with the ID of the two related nodes with the link properties. In the brain, types are encoded as a specific kind of node related to all thoughts of that type. In Neo4j, it is more efficient to convert those nodes to labels. Therefore, persons from the brain are nodes with a person label in Neo4j. Tags are also encoded as nodes in the brain, and they are left so in Neo4j. For example, nodes for deceased people are related to the deceased tag node. Nodes for people with a portrait in the brain are related to an attachment node with a file name as a property. The whole path to the file can be reconstructed from the brain export directory. As we've seen in the previous slide, for Gramps, we need an extra family node per couple. So we can use the graph topology to match a node labeled person and related to two other person nodes with a mother, a father relationship, to create a family node with a family mother, family father, and family child relations. This is a Cypher query that does that. If this is the first time you hear the word Cypher, just think of it as a database query language that is based on graph pattern matching. The two sets of relations with and without an intermediate family node are kept because they're both useful in different contexts. The data transfer process between the brain, Neo4j, and Gramps takes a couple of minutes. Since it's quite boring and we do not have that many minutes here, I'll skip the demo, just giving you an overview. First, you use the brain graphical interface to export to JSON. This produces a directory with JSON files. As just presented, we only use thoughts.json and links.json. Each thought has its own directory in which you find node attachment and portraits. Then you run a Python script to import this JSON JSON to Neo4j. And finally, you import reduced CSV to Gramps. Generating visualization with Gramps is done with a graphical interface. There are different options you can adjust, like the individuals you want to display the family tree of, whether you want children, parents, or both to be displayed. You can set a node background color for people with a certain family name, etc. Gramps visualizations are very useful, but they have their limits. Coloring of nodes according to family name is very helpful to find your way in a large graph, but it's very tedious to list names and color code with the graphical interface. Also, given the way I've input women's name with spouse name first, it does not work well if you want a women's birth name to be used for coloring. At first, as I was looking for people's common ancestor, I had to do it with prints and color markers to visualize those relations I wanted to stand out on the graph. In short, it is frustrating not to be able to use the power of Cypher queries to precisely select what you want to display, like, for example, ignore a specific person's descendant to make another part of the graph more visible. Putting manually collected data in a database with a graph pattern-based query language allows for covariance checks and to detect missing information and manual errors. Based on the graph topology, you can also compute new information. The number of children a couple simply is the outgoing relation from the node. After discovering information online about part of my family, we had no idea. I wanted to know, and I wanted to know. I'm stressed because I see that we're getting short of time, which makes not things easier. So yeah, I wanted to know how many cousins my great grandfather had. So you can easily calculate all this as well as more complex information with Cypher queries. Let me just quickly outline 2 examples of things you can do with the graph topology to extract specific information. We've seen how easy it is to drag and drop a death certificate URL in the brain to keep track of sources. This URL ends up as a location property of an attachment linked to a node with a deceased value for the name property. So a pretty simple Cypher query will get you the list of sources for death certificates. In a similar way, some regex pattern matching on the URL, you can extract the list of the genealogy website accounts that have been used as a source of information, which makes it the right moment for me to thank all people who share online archives and civil status registers that they digitalized and typed in. This project would not have been possible without these online resources. So now let's see what we can do with Bloom for to visualize such a use case.
Let's search a person, say my grandfather. The text displays his year of birth and generation. I'm 0, my grandfather is 2, etc. With scene action that are parameterized Cypher queries, I can display his descendant. You can access more information about each person by displaying the node properties and explore relations that connect to its neighbors. For example, you can see that my grandfather has 4 brothers and sisters, and that I've recorded one of his godfather's relation. If you add his ascendants, the display starts to be very difficult to read, especially because parents can be displayed very much apart. And if you display an even larger set, it gets even more messy. People in a line can actually be from different generations. So Bloom hierarchical algorithm is not very appropriate in this case, probably due to the fact that it does not take into account the topological specificity of a genealogy graph. There's a clear distinction between vertical relations, mother, father, child, and horizontal relations, like spouse, brother, and sister. Let's now look at the other graph model with direct father-mother relationship and no family node. Let's use the 4-space layout and find cousins who married each other. This is the graph topology for cousin. They are children of 2 brothers and sisters. So this is the Cypher query to mark the 4 relations involved to graphically identify married cousins. You match the children of brothers and sisters, and you check that the children are married. If so, you set a highlight property to red for relations involved. Now, if you refresh the data in Bloom, you can see here, for example, a brother and a sister whose children got married. This is done with rule-based graphical settings. Unfortunately, you have to manually set color with the graphical interface. The property value cannot directly be applied. In this use case, Bloom seems more appropriate to explore a limited number of nodes. Let's look at Elvish, whose one of the oldest ancestors are found on one branch. With another scene action, we can display the direct line between him and me. The enclavement of the valley where these people lived probably is the explanation why both my grandfather's parents, as well as a whole bunch of people from the valley, descend from this same guy, Louis. Louis here had a sister. And she married a guy with the same last name as her. This is something I find very annoying with Bloom. Whenever you add or remove nodes from the display, all nodes get automatically repositioned. I really wish I could decide when I want automatic repositioning and when I want things to stay as I manually, carefully position them. One thing I really like are action scenes. Let's use another one to find common ancestors to see if Helen's husband has a common ancestor with her. Well, not in the collected data, but Louis' wife also has the same last name. Let's see about her. And yes, there's a common ancestor between her and her brother-in-law. Visualization are useful to check data coherence. For example, as I was checking if the generation difference here made sense according to parent-children dates of birth, I realized because his date of birth was after his supposed mother's death, that I had one guy related to the wrong mother.
And
here is the URL to access the
was a
online
bit too
version
yeah.
of
It's
yWorks Neo4j Explorer.
Yeah, this is a demo of what you can do with yWorks on the same use case.
We have a local Neo4j database running. And so we connect to the database. First, we automatically get the database schema. And to extract information for display, we have two options. A graphic interface to select nodes by labels and property values. One feature I really love in this visualization tool is the template that you can create, not only to display any property value, but also to associate nodes properties to graphical representation. You can set the node background color according to a property, which means you can use all the power of Cypher to set the property in a very precise way that will be used for the background color of the node. You can optionally display a border or an icon according to a node property. Here, for example, the border only shows for nodes that have a highlight property set. And the black ribbon that indicates a person is deceased only shows if the death icon property is set. You can also display alternate icons according to the property value. For example, the gender icon contains the SVG code for the appropriate icon. I find it really great that in this way you can easily visually represent some categories that structure your data. Bloom has some of this, but you depend on the graphical interface to set size and color values. You cannot just use the value of the property. Unfortunately, in yWorks Neo4j Explorer, it is currently not possible to have relation templates. We will see a workaround to this in a moment. The second way you can extract information from your database is a Cypher query, which means you can do very fine-tuned pattern matching on nodes, labels, relations, and properties to precisely select what you want. For example, you can select a branch of your family tree by first marking a branch property for the nodes of someone's ascendant and descendant. That is, you match a person's node and set a branch property to true for all nodes related to it by any number of mother or father relations. In order to visualize the selected nodes with the template in yWorks Explorer, a field property is set. Now in Explorer, you can use a query that matches all nodes that have this branch property set. So here are all of Jean's ascendants. The display is not optimal because the spouse relationship confuses the algorithm. It will be much better if you hide this type of relation. To update the display, you need to re-extract the nodes. Let's now set the property to add the descendant of all these people. Now here you can see descendants in green. Then we can add spouses, spouses' children, and spouses' parents. The color set to the field property helps visually keep track of how people have been added to the selection. You can also use the field property to have a color per family. The limits between families is a subjective choice. In part of the family where you personally know people, you may want to find a granularity for family groups, but no matter your choice, with a Cypher query to set the property, you can display exactly what you want. With these colors, I can easily orientate myself in a large graph display by identifying family groups that are meaningful to me. Here are 4 unrelated nodes, which probably means I should get back to the data collected in the brain and check things out. There probably is a manual input error, a missing link, or a link type. This is one thing visualization are good for. Even with this many nodes, defaults will immediately stand out visually. For now, let's just delete these nodes. You have different possible layouts, but this explorer cannot turn the tree top to bottom. For this, you need yWorks online editor that you can open from this menu. Here you can change the layout with many different options. This editor allows to do something I miss a lot in Bloom, and that is to manually adjust nodes' position. Here, the colors immediately show that having these people so far apart does not make much sense, so you can move them to where it makes a more readable graph. It does take time, but you can get the exact display you want without starting from scratch, since the layout algorithm does some of the job for you. You have several graphical output formats. Note that for PDFs export, images need to be inline with URLs. There is a cross-origin issue. Visualizations can also be saved as a GraphML file. And the good news is GraphML is XML, so you can use XML tools to automatically adjust whatever you want to automate. With some Python beautiful soup, you can, for example, suppress those link in, link out display that do not make sense in this case. This is also how you can automatically color some relations according to property set with some Cypher queries. Here is, for example, how to show common ancestors of people with the same last name.
And so as a wrap-up, I'd say, oops, let's get to the last slide. Yeah, I say that with this genealogy use case, we've seen that graphs are very interesting to collect and structure information intuitively as it comes. Recent development of graph technologies allow to apply automatic formatting, coherence checks, and corrections on such manually structured data. This way you can get the best of both human thinking and machine processing combined. Different visualization tools are best either for local information collection and structuring or for large overview to make sense of complex data and distant relations. And with this, I thank you for your attention. I'm afraid I'm short for the questions, but I'll be around in the chat. So
Very cool. Thank you very much, Veronique. It was very interesting. People liked it as well. So here, for example, Tony, great use case, very applicable, great flow of explanations. So it was nice. And also here, Walter, making the graphs vertical makes them much more interpretable for genealogy. It's nice to do with one click. And toggling the automatic rearrangement on and off is also a nice feature. So that we can only agree to. And then maybe we can do one question or another here, super cool from Brent. Is from Tony, was that at 360 of the model? I think that's basically what you did, right? You showed us all the way around your genealogy model from basically from beginning to the end.
Yes, I'm not sure I understand what it means by 3600.
So full.
Yeah, I was it was the full model from the model of the brain, that is the applications model, and that's the same for whatever data you fill in. You have this structure with thought types and tags, and you can extract that on different kinds of data, and then you had another model for Gramps. So Neo4j helped convert the models.
Cool. All right. Well, that is the end of this. Like Veronique said, if you have any other questions, she's around a little bit longer in chat for later on. Otherwise, the deck had her contact information. So thank you very much, Veronique, for presenting today.
Thank you.